So, going to look at this idea of multiple roots and a way of finding these. Now, here's the interesting fact. If you know you've got a multiple root at x equals a, say, then it's also going to be a root of the derivative, order one less. If you think about that, parabola, okay, we know it has a double root there at the vertex. Now, if you were to differentiate your parabola, you get a straight line, y equals 2x, which also has a solution at that point. In fact, whenever you differentiate, all that happens is you take a power off. So if it was a triple root, when you differentiate it, the derivative, if you were to draw the picture, there'd be a double root there, and so on and so on. And that's all this is really saying. So if I know it's a root of multiplicity m, I know that when I differentiate it, that picture would also have a root there, but of multiplicity m minus 1. So let's prove that. So I've got a multiple root at a, so I know there's a factor x minus a to the power of m times some polynomial. Now, that other polynomial, I know x equals a will not be a root, otherwise its multiplicity wouldn't be m anymore, it'd be m plus whatever. And we're saying it's a multiple root, so m is bigger than 1. So if I differentiate that, write down the first, diff the second, plus write down the second, diff the first. Okay, there's a little bit of factorising that can happen there. There's a common factor, x minus a, and whenever we factorise, we take out the lowest power. So x minus a to the power of m minus 1, it factorises, and what we're left with is x minus a times whatever the derivative of qx is, plus m times qx. Well, obviously I don't know what that is, but it is a polynomial. Because if you differentiate a polynomial, you're going to get a polynomial. So q dash x is a polynomial, x minus a times it will still be a polynomial, and m times qx will also be a polynomial. More importantly is this factor out the front. There's x minus a to the power of m minus 1. So we have a root to the power of m minus 1. And if I look at my interesting expression here, a is not a solution to this. Yes, if I sub it into x minus a q dash x, I'll get 0. But remember, the whole thing has to be 0. And we said a was not a solution to qx. So I know that can't be 0. So the overall expression in there is not 0. So a is not a solution to that second expression. So in other words, I could write it as x minus a times some polynomial, but I know a is not a solution to that second polynomial. So yes, its multiplicity is 1 less, m minus 1. So we've been given a bit of extra information to help us solve this particular equation. We're told it does have a double root. Well, that's a cubic. Now, if I know it's got a double root, it's also going to be a solution to the derivative. The derivative of a cubic is a quadratic, and quadratics are easy to solve. So the first thing I'm going to do is differentiate it. So I know the double root will be a solution to the derivative. Solving that, it factorises nicely, 3x plus 1x minus 3. I get two possibilities. Now, they're not both going to be double roots. So remember, not only is it a solution to the derivative, it's got to be a solution to the original equation as well. Now, logically, I think one of those would make sense. Which one?
3.
Why not the minus a third? Yeah, because if you had x equals minus a third, you'd be expecting a factor of 3x plus 1. And this is a cubic. This is a monic, I should say. So, yeah. But, you know, it might have been one of those weird ones where it's gone x plus a third. But if I had to pick which one I'm going to try the x equals 3. It's the logical one to choose, I think, in this one. And sure enough, when you sub in 3, you do get 0 into that. So, all right. I now know it can be factorised x minus 3 squared. The other factor must be linear, because it's a cubic. So if I've got a quadratic, got to get to the power of 3, so it must be a linear factor. Constant times constant equals constant. Minus 3 squared is 9. Well, 9 times 2 is 18, so there's the other factor, x plus 2. So now I can go and solve that equation. X equals minus 2 or x equals 3. Remember, there is a subtle difference between saying solve this equation and find the roots. If the question said find the roots, x equals -2 or x equals 3 is not the answer. What's the answer? -2, 3 and 3, because 3 is a double root, so it would appear twice. Okay? So that would be the difference between solving the equation and listing the roots. Cool question. Because, look, it's one of those ones which are nice and symmetric. Look at the coefficients, 1A, B, A1. But what makes it even cooler is look at the year that the question was in. It also has that pattern of 9. So that, cool question. All right, so we're told alpha is a root of this particular quartic. And 2 plus b squared can't equal 4a squared. This will come in useful, I'm sure, later on. We'll see how. We're going to show that the solution, the root, whatever you want to call it, can't be 0, 1 or -1. So those three numbers cannot be solutions to this equation. Well, 0 is fairly easy to do. I just sub in 0 for the factor theorem. It turns out to be 1. We know for it to be a root, that would have to have been 0. So, okay, can't be 0. Can't do the same with 1 because when I sub in 1, I get this 2a plus b plus 2. Now, I don't know what a and b is. So I can't, with 100% confidence, say that's not equal to 0. Well, can't say it yet. Let's see what happens with -1. If I sub in -1, I get -2a plus b plus 2. And again, I'm not sure whether that equals 0 or not. Hang on a sec. They told me this. 2 plus b squared cannot equal 4a squared. So that means b plus 2 cannot equal plus or minus 2a. Well, if b plus 2 cannot equal minus 2a in this first one, that can't equal 0. And in the second one, if b plus 2 can't equal positive 2a, well, that can't equal 0. That's what the extra piece of information was for, so we could go and prove that. So plus or minus, I'll do it all in one hit, plus or minus 2a plus b plus 2 cannot equal 0. So therefore polynomial 1 can't equal 0, polynomial -1 can't equal 0. Alright, so we now know it can't be 1 or -1. Now, why is this important? Have a look at the actual polynomial, and we're saying 1 or -1 can't be a solution.
On complex roots.
See, the product of the roots are 1. And it's monic. So we're kind of expecting integer solutions. And if I can't have 1 as a factor of 1, or -1 as a factor of 1, then I've probably got complex solutions there, or imaginary ones. So, but anyway, let's see. We're now going to show that 1 on alpha is a root as well. Well, if I sub 1 on alpha into the polynomial, we want to show that this is equal to 0. Algebraic fraction, let's see what we got. Put it all over alpha to the power of 4, the top of the fraction. Well, hang on a sec. That's polynomial alpha on the top of the fraction. And we know alpha is a solution. So polynomial alpha is equal to 0. Well, 0 over anything is 0. So, yep. 1 on alpha is also a solution. So if alpha is a solution or a root, 1 on alpha will also appear as a root. So every time we see alpha, we see 1 on alpha. So now we're going to deduce from that. If alpha is a multiple root, its multiplicity must be 2. But further, and more interestingly, we're also going to show that 4b is equal to 8 plus a squared. That's the more fun bit. Right. If alpha is a multiple root, remember we said whenever alpha is a root, 1 on alpha will appear as well. It's saying alpha is a multiple root. So alpha must appear more than once. So if alpha appears twice, 1 on alpha must appear twice. That gives me how many roots? 4. So I've got 4 roots. It's a quartic, so I can't have more than 4. So therefore the only possibility is that its multiplicity is 2. Thus, no root could have a multiplicity of greater than 2. The more interesting bit, if I now know it's a double root, it must also be a solution of the derivative. So the derivative of our particular expression, 4x cubed plus 3a x squared plus 2bx plus a, we know it's a solution to that. So the roots of this expression, it's cubic, it will have 3. Alpha will be a solution because it's a double root. 1 on alpha will be a solution because it's a double root. There is a third solution that I don't know what it is. I'll just call it beta. So the 3 roots, alpha, 1 on alpha, and some other one, beta. Sum of the roots, minus 3/4 a. Sum of the roots, 2 at a time. We get half b. Sum of the roots 3 at a time, actually the alpha and the 1 on alpha cancel out nicely with that one. So I can actually work out that third root of the derivative is a minus 1/4 a. So I should now be able to work out something. Let's see. If I substitute the third one into the first one, in other words, substituting beta into the first one, I end up with alpha plus 1 on alpha is minus 1/2 a. Okay. If I substitute it into the second one, so basically I'm eliminating beta from all the equations. Eventually, let's have a look. I get 1 minus 1/4 a alpha, minus 1/4 a, 1 on alpha is 1/2 b. Well, those second two terms have a common factor of minus 1/4 a. Inside I get alpha plus 1 on alpha, but hang on, over in the left hand side here, we said alpha plus 1 on alpha is minus 1/2 a. Sub that in, I've now got rid of the alphas as well. And so now I can play around with the expression and rearrange it to make it look like what they're asking us to show. So I've got 8 plus a squared is 4b. Time to play.